going over the quiz until Wednesday when I hand it back. It was a straightforward quiz. There's nothing tricky about it. And today, like we have 2 weeks of classes left. We have today, Wednesday, Friday this week, and then Monday, Wednesday, Friday last week. And last Friday, what I'd like to do, I know we usually have a quiz, but I wanted to just do a review. So assemble your questions and everything like that, and we'll do it then. But we're doing fine as far as material we're supposed to cover in the time allotted. So the last thing I wanted to talk about in chapter 9, the MC chapter, is going to be common mode chokes. And these are something you're going to find out are very handy. You'll run into it all the time. You'll run into it. I'm trying to think of how many different devices you'd run into it. Anything where you can get a common mode current. You all know what common mode is? Let me explain this. There's common and differential mode. First, this is going to be common mode chokes as the topic. All right, and I'll just tell you what they are. In Dr. Whitmore's book, he shows you basically they have a piece of material that's like a donut, and it's made up of a ferrite. It's got some mu, where mu is much, much greater than mu naught. Typically, when you talk about these things, it's usually iron. Doesn't have to be. And then what they'll do is put a coil of wire around here, and it'll have N turns. And then they'll have a second coil of wire here. And this will have N2 turns. Typically, N1 is N2. Typically, N1 is N2. But it doesn't have to be. I've actually wound these. Now here's how it works. I'll show you it in the circuit, but I just want to go through this. If you look at this, and how many have had Gross here for power? Gross does this. He does it with the flux linkage. He does this kind of stuff. Here's, let me step over here for a second, make sure everybody understands when I talk about inductance in general, how to get it. If you just had an infinitely long straight rod, it's going to be a ferrite rod, so the mu here is large. In this material, just a rod. And I wrap a set of turns, call it N1 here, and I put a current I1 here. Now, how many remember seeing this stuff? Gross thing. Right, I want to make sure you're all clear on this. Well, the way you find the direction of magnetic flux, we could show you a magnetic circuit. Y'all remember magnetic circuits? I could show you a magnetic circuit, but if we just assume this is infinitely long and had some measurable reluctance that's not infinite, we'd say that we'd get a flux in this direction. That's called a magnetic flux, and this is in coils 1. Do y'all follow me? Right. In the right hand rule, you just take your right hand, take your index finger, put it in the direction of the current, and then grab it. So if it was going in the other direction, the flux would be going this way. You all with me on this? All right. Now if you have a second set of coils, this is where the dot convention comes in. What Charlie Gross will do, and I do too, is say, where the current came in the first coil, you dot it. Now, if you choose here, this is I1, you choose I2, you're going to have, there's N1 here, N2 here. If you put an I2 in the second set of coils and the fluxes are in the same direction, in this case they would be, the flux from 2 would be the same as the flux from 1. Do you all agree with that? Because I got the coils wound the same way. Then you put a dot here. This is how you get the dot convention. Now, I'm not going to get the actual inductance, but you all remember doing that, right? If, pray chance, I decided, suppose I said, well, I'm going to put the current in here, and the fluxes wouldn't align, would they? Then the flux in the bottom one is going to be going down and into. And whenever you get opposing fluxes, you dot the opposite terminal. That's how you get the dot convention. And that's the simplest way possible. Now, it's important to remember that. I'll get to the equations that govern this. So back to this. This is just that, only now I bent one of these two downward, and I have a closed circuit. You with me? So here, I have a current I1 here, and I take a look at this, and therefore the flux would be flowing in this direction. Make it a little bit better. Y'all with me? So now I've got to find, I put a dot here. Now I got to find the dot convention on that one. I normally just take the top and I put current in. When I put the current in here, well, which way does the flux go? Is it in the same direction? Yes, right? They're circulating, correct, class? Mm-hmm. So therefore the dot goes here. That's how you get the dot convention. Remember how to get the, I mean, we're not going to do this. I don't expect you to know. Remember how you get the magnetic, to estimate the inductance of something like this, anybody? Self-inductance and mutual. Do y'all remember?
It's turns and reluctance.
You're close. Normally what they'll do, and I'm just going to show you self-inductance, mutual is just as easy. Now you don't have to, you're not responsible for this, but this will help you appreciate what I'm showing you. So if you just have a single core like this, I'm trying to draw this a little bit better. A single core like so, with some mean radius omega or rho zero, and it has a cross-sectional area A. Now A, it doesn't matter how you get that. I could give you a radius for that core, and you could figure it's pi A squared. But you all follow me on this, class? Doesn't matter. And it has some value of mu. Then I come here and I wrap it with turns. And I'm going to say I have I have n turns here. And I'm going to put a current I here. I only did one set of coils because I'm going to get this self-inductance. With me? All right. Well, I can see that really this is a simple magnetic circuit. And since I assume I can figure out what mu is, it's just mu relative mu zero, I can say I can draw an equivalent, quote, electrical. It's really a magnetic circuit only with an electrical look to it. This becomes Ni. That's called a magnetomotive force. Right? Do you remember that? It's just like EMF is the electromotive force. It's just like a voltage. And then you have a reluctance here. Jacob said this, right? And the reluctance is always going to be proportional to the total length for a single element here with a constant cross-section. Inversely proportional to mu, and inversely proportional to the cross-sectional area. It's identical to the resistance formula for constant cross-sections, L over A, except instead of sigma, you have mu. You all with me on this? Now that's the reluctance. How many remember this? I mean, at least you're acquainted with it. You don't have to remember everything. Do you remember this? Okay. So now the thing that's akin to current, normally we call this I, but that's really the magnetic flux. And the magnetic flux would be like the magnetic voltage, Ni, divided by the reluctance, right? Y'all remember that? All right, now once you have that, then you can find the inductance, because the inductance, this is the self-inductance, is really the amount of flux going through one turn. So it's really that flux, right? times the number of turns, correct? So now it's times N, and then it's divided by I. You'll hear this called the flux linkage, and that's a typical symbol for the flux linkage. It's the amount of flux through one loop times the number of loops that the flux penetrates. Then when you divide it by the current causing it, you get inductance. For this one, you can see this is the self-inductance. It would be what? Just N I over the reluctance times N, or N squared, right? And inductance is always proportional to the square of the number of turns. N squared divided by the reluctance. And that's the way it always is. Now you see, that's the self-inductance, right? To get the mutual, the only difference would be what? Are y'all with me on this? I don't hold you responsible for calculating this, but it helps to appreciate this for where we're going. Because we wind these ourselves, by the way. A lot of times we have these small little cores, ferrite cores, and we need a certain value of common mode choke. It's much easier to just wind them yourself. So if y'all good with that, right? Now, when you have that's what happens. That's how you calculate the self-inductance. It's just N squared of the coil over the reluctance of the coil you're talking about. Now, if this is N1 and this is N2, like so. Now, if you want the mutual inductance, you find the flux that's actually going to be going through the secondary coils caused by the primary coils, right? And again, that's just equal to N1 in this case, right? Times I over the reluctance, right? And then you have to multiply it by the number of coils that it goes through, right? That's the flux through one. There's nothing connected, no load out here. So now I multiply it by N2. And now that's the flux linkage. So when I take this times N2, that's the flux linkage. And when I divide it by the current causing it, now I get the mutual, which is N1, N2 divided by the reluctance. You'll notice that this would be the mutual in the self will be identical technically if the number of turns are the same. Do y'all see that? Now here's the truth. They're never quite exactly the same. And here's why. They're not showing you this, but there's fringing fields. Like some of this, if you actually took a look at a B field line, there would be one that comes outside there. Y'all follow me? So not all the B field is related to the flux, right? The integral of the B field over the cross sections. Some of this stuff, even though it's a small amount, is spurious, comes out. So you don't get perfect flux linkage. That's one of the reasons. And other things are just imperfections in coil and wire and things like this. There may be an asymmetry, so you just have to appreciate that fact. But generally speaking, if anyone is into it, you're just about got the same. Maybe not exactly, but real close, okay? And that's what you want. Now, when we talk about why I spent time doing this, y'all realize that that's basically a transformer. You've had transformers, haven't you? Did y'all, if you had transformers, raise your hand. I want to make sure, because one time, did you have transformers or not? Transformer, V1, V2. Remember, it's V1, I1 equals V2, I2? No. What class did you get them in? Circuits? Have you had power?
Yeah.
And you've had power? Okay, you should have had them. Maybe the word's not ringing bells, but you'll see with the equations and what it looks like. So, now I'm going to show you the circuit that goes with this, and this is just the schematic. That's the physical device, and we wind these things all the time. Sometimes we need like maybe 10 millihenries or 10 microhenries. So we know what the core's value is. We know the mean radius. You know the area for these little cores. If I can, I'll bring one down. And we just figure how many turns we need. Now remember, that inductance goes up as n squared, so it's not that many turns. And we just wind in the primary, wind in the secondary, we do this. Now, when you look at common mode choke, the way it works is this. Then I'll go through the equations. That thing I just showed you right there, here's the dotted terminal. And then here's the dotted terminal here. And there's going to be some mutual. And I'm going to assume, just because it always is this way if it's a common mode choke, I'm going to assume this L is this L, all right? It just always is. And then I'm going to say, well, this has a current, some I1 and some I2 flowing through the bottom one. Okay. Now, here's the deal with a common mode choke. We know in the real world, when we have an extension cord or any kind of common device used to communicate power or information, we work in what's called a differential mode if we're just using two conductors. We have current going down one rail, coming back the next. Y'all with me on this? That's just the nature of the beast. Current doesn't flow in the same direction in both things. That's bad. However, it does happen. Let me just show you the badness right here so you can appreciate it. All right, if we just think about this as a standard thing, let's make it real simple. Let's put this resistor over here, R, load. And that represents some input to a device. It could be an FET input without the capacitor. It could be very large. Now we have something over here. Say we have a signal. And then this is V of the source. And everything is fine, right? Current. If I got a source here, it's felt across here. And the current through RL is just the source voltage, if it's a short thing. Source voltage divided by Vs, right? Now here's where trouble comes in. I'm not showing you something. But when you have these things and there are lightning strikes, for instance, when lightning hits something like this, oftentimes it's not one wire, it's both wires. There's a lot of reasons. You can get this with actually the inductive effect too. So now there's going to be a current. You can assume this comes from anywhere. I'll just call this I common coming down here. Or I lightning, how about that? Well, some of that goes this way, some of that this way, some of that this way, some of that this way. But the point is, this is going to be a common mode current that's flowing there. Y'all with me? Now, why don't you want that? Because when this is flowing down here, I'm not showing this to you, all this current wants to get to ground somewhere. And the way it gets to ground usually is it destroys something inside of that device to get to ground, to get to the actual earth ground. That's the reason common mode is bad. Because when the current, matter of fact, I have talked to people at Adtran, Adtran, they make a lot of stuff that are devices that go in, like for cell phone towers and stuff like this. And they have inputs, almost all the inputs like from Cat5 cable and stuff like this it goes through a transformer. When lightning hits, lightning comes down there going the same direction on all the, basically all the connections. And it gets there and it wants to get to ground. Guess what it does? Well, it basically, destroys the insulation of the transformer. It goes right through the circuit board if it's there, and then goes to ground, and it utterly wrecks the system. Y'all follow me on that? So if you can stop that, it's good. Common mode currents are horrendous. How many of you have heard of common mode currents? Common mode is when the current is in the same direction on two connecting wires that connect like source to load. Differential is the normal way. We like differential. Got it? So this common mode choke is going to do this. It's going to develop a lot of voltage right across here to prevent the actual common mode currents, but it's going to allow the differential mode currents without any impedance. And I'm going to prove this to you. So that's the idea. Anything going sloshing back and forth it likes it, and I'm going to show this to you mathematically. Anything that tries to go in the same direction, it blocks. There is one caveat I might as well say about this. If you think about this, now, I almost don't want to use lightning, but I'm going to use lightning. Lightning has an enormous amount of voltage that what really happens is you have this ball of charge. If it's cloud to ground, it's usually negative charge coming to ground. Technically, current's flowing this way. It doesn't matter though. When you have a large current, this is billions, maybe hundreds of billions of volts, right, caused by this charge. Lightning comes down. The lightning acts like just a good conductor. So you got billions of volts, think of it that way, that's driving this thing, and it hits. Well, if you got something that's got a force of billions of volts, then you need a tremendous number, you need a huge arc over. You've got to prevent arc over. Suppose this thing does try to stop that current, but we're dealing with something that's got 1,000,000 volts. Follow me on this? Well, then we just, so what you have to do is have a large number of turns, oftentimes if it's electrically related to lightning or large voltages for common mode. However, there's other ways to do. Did Gross ever go through lightning protection too, Dr. Gross? Here's the big deal with lightning protection with power systems in the real world. And I'm just telling you this because this is stuff you got to realize you're probably going to need to know. If you're going to deal with real stuff, I mean, if you're going to be one of these guys that makes a lot of money out there, where you got to bring things to life in the field, I mean, you design them and then you're the guy that's responsible for bringing them, have them work in the field. And it's not just a piece of software that's standalone. What you have to realize is when the lightning hits, we don't just have common mode. What we do, as soon as lightning hits, we detect a surge in voltage with respect to the ground. As soon as that happens, when it goes above a certain threshold, it becomes a direct short to ground for a time. Have you ever seen the lights flicker? What's going on with the power company in a nutshell is they have lightning protection. So they know a huge over voltage is happening. There's going to be a current surge. Rather than that going through the transformers and blowing them up, they'll short that to ground. And so when the voltage goes above a certain point, it'll literally trip a switch and it'll cause it to short to ground. Now, without getting into all devices, there's devices that are vapor tubes, there's ignitrons, there's all sorts of devices. They can have pins, maybe a couple million volts on them before they actually arc over. But when they want to arc over, they just have to put a little voltage on an element that would heat some mercury up, and it shorts right out. I use these with my railgun. When we were doing the railgun project, I learned a lot about this. There's also solid state devices that'll do this, but you got to remember this. If you're getting really large currents voltages from lightning or something like that, and you want to stop common mode, you have to provide that thing a way to short to ground. And that means for at least an instant, you take your communication or your power offline and drive it to ground. They always blink for an instant, sometimes twice, because there's usually there's a cloud to ground, the first one, then there's a follow-up oftentimes. There's 2 or 3 strokes that'll bring it, but just watch next time. When you're at home and you see your lights flicker, see, fluorescent a little tough, but if it's an incandescent light or an LED, you'll see it flash once, twice, a lot of times, maybe 3 times at the worst, and then it stops. And then a little bit later, you'll hear the thunder. So, just trying to tell you, common mode currents are bad. The way we do this, I'm not going to get to the point here. The way we actually deal with this, we say that we're going to have a voltage, and we'll call this V1, plus or minus V1 here. I know I'm spending a lot of time on this. And we're going to have some plus to minus V2 here. Now, remember, this is a transformer. It's got a mutual inductance and a self-inductance, right? And you remember back in the day when you had transformers, that whenever you had a transformer, they usually talked about some L1, put a dot here, plus to minus V1. Actually, these would be better to be called magnetically coupled circuits. It's better to call it that because transformers assume your efficiency is just about perfect. And then you had winding here, L2. I'm going to make them both the same because that's always the way it is. And then you're going to have a mutual inductance M, right? You're going to have some current I1, and you're going to have a current I2. And this will be plus to minus V2. Now you can see I just took this and I flip it that way because that's the way you're used to seeing it. Y'all with me on this? I'm trying to make it easy to understand. All right, now this, if you remember this, the way it works, and I'm going to go to the, I'll go to the time domain and then the frequency. You don't need to write this. I'll tell you what to write. Just watch. When I look at V1, right, technically V1 is equal to L dI1 dt plus M times dI2 dt. Y'all remember that? That's in the time domain. If I look at V2, better yet, y'all give me this. If we're at steady state at a constant frequency, what I can do is pull out a J omega, right? If you have DDT, right, and you're in the frequency domain, it just pulls out a J omega, doesn't it, class? So what I can do is just write this thing as V1 is equal to, and I'll call this L1, is equal to L1, actually J omega L1, L1 times I1 plus J omega M, the mutual will be the same, times I2. That would be V1, and V2 would be identical, only I1 would swap with I2. Do you follow me? So the way I like to write this to keep everything consistent is I can say that V2, normally it would be L dI2 dt, the self, it would be the EMF caused by the time derivative of the current into the inductance itself. But I'll just call it J omega, and here I'll use the mutual first, M times I1 plus J omega L times I2. Now the reason I did this is so I have I1 and I2 vertically on top of each other, and I can create a matrix if I want very easily. Follow me? And the way I can write that is simply V1, V2 column vector is equal to J omega, and then it's going to be equal to L, M, M, L, I1, I2. If you look, we'll assume here that L1 is equal to L2. All right. And again, I'm just putting this down here for everybody's sake to see. You've had this. So when I take a look at this, I want to see, those are the equations that govern it. They govern this too. I just put them that way because you're used to seeing it that way, right? Here's V1, there's V2 as I've drawn. So I say that I1 can be composed of both a common mode current and a differential. Now the differential is flowing that way. And I can say I2 is composed of a common mode current minus a differential, because the differential is going to be in the opposite directions. Do y'all follow me? There's going to be a common mode here that's added to ID. They're both in the same direction. Down here, the common mode is still in the same direction, but you subtract off ID. And these are two actual values. Do y'all follow me on that? They're time varying, and they're assumed to be at a constant frequency. So now I go through and I show you what the actual impedance is, or I show you what the voltage is, V1. First for the common mode, I'm going to do it here. So this is for the common mode. And I want to get V1. So remember, V1 is equal to J omega L times I1, right? And it's plus J omega M I2. Y'all with me? Now here, I'm just taking a look for common mode. And if I'm just looking at common mode, I1 is equal to I2 is equal to I common. You follow? I'm not even looking at the effects of this filter on the differential, just common. Do you see that? You go with that, Jacob? All right, I want to get V1. All right, now that means V1 is equal to J omega, and then it's going to be L I common, so it's going to be J omega L I1 plus, or really, I common plus J omega L I common plus J omega M I common, or it's simply J omega and it's L plus M I common. Now this is just V1. Do y'all see that? Now if I want to think about an equivalent impedance of that, if I had V1 over I1, or I common, pardon me, that would actually just be J omega L plus M, wouldn't it? And that would be the impedance of just this element. Now you can make an argument for symmetry that the impedance of this element would be the same, correct, class? So it'd be twice that. Do y'all follow me? So I could say the total impedance of this circuit, or I can call it Z common of this circuit, which is just a common mode choke, would be J omega times 2 times L plus M. And that would be the effect of this and this. So you could stick in just one impedance of that value in there in series with that, and that would basically, that would be the effects on common mode. Y'all follow me? Now remember, these two are going to be close together. Now let's take a look at the effects on differential mode. This is the critical one, because I can make this thing fairly large. And the omega, what I haven't said is when you do common mode currents for transients like lightning, it's not at one frequency. There's a whole, I mean, it's basically an infinite, you take a standard current waveform transient, you turn it into a Fourier series, and then you use this as the impedance and get the current. And I don't want to go there now because that's a little too far afield. But y'all follow me on this? Now we come over here and now we do the effect on the differential mode. And lo and behold, when I do that, I say that I1 is equal to I differential and I2 is minus ID. Do y'all follow me on that? Because it's going in the opposite direction, right? I1 and I2 dictate the directions. So now I look at V1, and I have V1 is equal to J omega L times I differential. But this is minus, so then it's minus J omega M times I differential. Y'all follow me? Now I factor out ID. I don't care about the magnitude, but now I take a look at that and I get J omega, right? Then it's L minus M ID is equal to V1. And if I look at the impedance of this, V1 over ID, it's J omega L minus M, not plus. Y'all see that? And if L is just about M, it's about 0. Y'all see that? So it doesn't stop differential mode. That's very important. And if you take a look at the total impedance, call it Z differential. Now that's equal to J omega times 2 times L minus M, which can be just about 0 if L is about M. I'm going to give you a few problems on this, but are you all good with that? And that's how you do it. So if you wanted to see the effect on the differential mode, if I put this in here, and I gave you M, gave you L, gave you the frequency, and then you put in a load here, some ZL, the only thing you would do is you could replace both of these with 1 and just put in J times 2 omega L minus M if it's differential, or J omega L plus M if it's common. Y'all follow me? And that's it in a nutshell. So that's common mode choking. You'll find that that's very, very useful. Now, I'll give you some problems to work, but I think you can handle these. When Dr. Wentworth spoke, what he's going to say is this is 0. Well, it gets close. It's not actually 0. In this, the common mode is large. Well, it's really not large. Normally, L is about M, so it's about 2L times 2 is about 4L. Normally. But I'll give you a few problems that are a little better than some of the stuff Dr. Wentworth gives. It gives you a little more room to think and sort of get you comfortable with that concept. So now we're into the next chapter, which is chapter 10, and this is microwave. Now, whenever I hear the word microwave, the question everybody should ask is, well, what frequency range is microwave? I say microwave is normally about a gigahertz on up. You know, you can argue, you can Google it, but when you talk about microwave engineering, you're talking about something where your gigahertz and the wavelengths are starting to get down. When you think about it, a gigahertz wavelength is 30 centimeters, a third of a meter, right? A lot of times with microwave engineering, you're down to millimeter waves. You're talking about small wavelengths, which means transmission lines can get real short. Y'all with me on that? And also you can communicate a lot of information. Without spending too much time on this, you've had communication theory, right? All right, do you remember with COM, one of the things you found is that, like for AM, your frequency spectrum had to do with the actual data that you were transmitting. If it was voice or sound, it was for human ear at least up to 20,000 hertz. So when you broadcast AM, you had to have plus or minus 20,000 hertz bandwidth if it's AM, right? Now for FM, it changed a big deal, didn't it? Because for FM, you had did he go through the Bessel functions that you get out of that stuff? Well, it can be anything. It has to do with the modulation index, right? You can have an enormous bandwidth in FM if you want. The FCC doesn't allow it. With microwave engineering, generally speaking, the rule of thumb is the higher the frequency, the more information you can carry. And I don't know if Dr. Tugnay did information theory with you. You know, there's a theory that says if you have any signal and you can look at it and mathematically they can say the amount of information that's in that signal. Did he go through that with you? Well, a lot of it, believe it or not, when you take a look at the transform of that, it goes into how wide the bandwidth is. And sometimes you'll hear the ability to transmit information. They'll just say, well, the bandwidth is very wide. And they assume you know that means they can take a lot of information and throw it down. You'll hear that interchange. If I get a chance, I'll go through that with you. So what do we talk, when we talk about microwave circuits, what do we mean? We mean circuitry that's mounted on something that are very thin boards that look like this. So when we talk about microwave engineering, and this is microwave. What you're normally talking about is a board that has a copper top. So it's got a thin layer of copper clad, they call it, right here. And then they have a dielectric material with some epsilon relative here. And then they have another piece of copper. So you got copper on top and copper here. It's a square board. Well, not square, but it's a flat board. And there's a thickness, call it T right here, of the board. So you got copper on bottom, copper below. Looks like a capacitor. That's what it does. It looks like a capacitor. So what they'll do is this. The bottom one, since it's copper, is almost always grounded. There's copper on both sides of this board. Have you all seen Duroid board? Do you know what I'm talking about? Do you know what FR4 is? The green stuff? The amount? FR4 is green and they have right on time, scan likely. Talked to my 8 o'clock class. One kid said I get 5 of these calls a day from different numbers. You can block them all you want. As long as they got your number, they can change. So anyway, back to this thing. Remember, copper top, copper on the bottom. Now, you've had something about lithography when you had solid state, right? When you had your microelectronics. So what they'll do is they'll put some kind of material, it's called a photolithographic material on there. They'll let it harden, and then they'll develop it. In other words, they'll have some way of turning the pattern onto that. And they'll etch off pieces of the actual photoresist, and then they'll dump it in acid, or they'll dump it in something that eats away the copper, and you'll be left with lines. It's called patterning. So on the top, you'll have like flat, thin lines of copper of a certain height. Y'all with me? That will connect circuits. Most of the top of the board will be vacant of copper, but there'll be connections. So what, if you actually looked at the side, just the side view, you'd see on top of this, you would see this kind of a deal, where these would have a certain width, a very thin height, and I call it H, and then the thickness of this would be T, that has some epsilon relative, and this would be grounded, and there would be a layer of copper on the bottom, but there would be lines of copper. And if you look down from the top of that, it would go like this, and then this, and this, and they would connect to like the base of transistors or the gates of transistors. All right, follow me on this, class? So they're really, what I'm doing with this microwave engineering, I'm just getting a lot of interconnects between different circuit components or antennas or transmission lines. And on this thing, these things are going to be longer than 1/10 of a wavelength, so they're actually transmission lines. Do y'all follow me? But the transmission lines are working in the TE mode or TEM mode. So it's transverse electromagnetics, not a waveguide mode where the things are bouncing around. It's all TEM mode, all right? Anyway, that's sort of the game here. And if I can, I'll bring a board in. I used to get them from Joe Haggerty. He's retired. But I'll show you what these things look like. They're very thin. They've got copper on one side, copper on the back. And then they've got a dielectric material. Now that dielectric material is a very low loss material. So they can send signals. They don't have to worry about a lot of dissipation in the board material. And I'll just tell you this in Dr. Wentworth's book, if you have your books and you look at the first part of chapter 10, he's going to give you a lot of information about how to estimate, for instance, the capacitance or the impedance, characteristic impedance. I don't worry about that. I'll tell you why. Because the impedance of these lines, this would be the characteristic impedance, has to do with the ratio of width to height. Right? Width to thickness here. And there are a cajillion formulas out there for that, but they're all canned formulas. They don't come from first principles. Somebody didn't solve Maxwell's equation, and this is a closed form of the solution, at least not that's used. They have something that approximates the solution of the impedance based on W, the height. And let me just give you a little more information about this. Years and years ago, when I was doing work in the area of microwave, we decided to investigate the effect of an edge. For instance, this line, if it has a characteristic impedance of say Z0 here, it's got it right in the center of the board when it's away from everything. As it gets closer and closer to that edge, it changes. It's called the edge effect. And that becomes significant. Now, the reason you'd like to know that is because when you're doing designs on a board, you have to route lines near that edge parallel with it. It's inevitable. You try to cram as much stuff as you want in it. So what we did is I ran a finite element solution to this stuff. So I solved for the characteristic impedance. And then for all manner, like we had that line with almost at the edge, and we moved it closer to the center where finally the characteristic impedance didn't change. And that's for a certain ratio of the width of the line to the thickness. And for a given epsilon relative. And we chose the most common epsilon values, the most common things, and we developed what's called a family of curves. And then you've heard of these things, we found a mathematical model that approximated that. This is the way it's really done. And so I published a paper in, I'm not sure if it was MTT, one of the journals, microwave measurements and techniques, or it was an EMC journal, one of the two we published. And we did this where the only thing we did was we found out approximate formulas for all the characteristic impedances that people could use, and that was valuable to some people. And I learned a lot about how all those formulas in like Stu's book and other books, they aren't really used. You know how people do it in the real world? They have a little tool and they just go in, and you've seen these things where you don't go through the design work yourself. If you want some parameters as far as the geometry of devices, you put in the characteristic impedance you want, you put in the constraints, the epsilon relative, and you can pick one if you want, or you can pick W or pick the thickness, and bang, it'll find all the other values that you need. And that's what's really done. That's the reason I don't spend any time on it, all right? I'm going to give you a few problems on this. It's suffice to say that with this stuff, for microwave stuff, that he has pictures on page 543 of what I'm trying to show you. He uses H and not T. He just shows you one line. He shows you then the field lines that would be present when you actually, this would be the E field lines as there. And he mentions one thing that I don't spend much time on page 545. He says all these things have an upper frequency where they'll act like an actual transmission line. And above that, then they don't act like a transmission line. They start acting like a waveguide. Because now all of a sudden, the thing electrically is getting to be of the order of a half wavelength. And then you get that bounce kind of stuff. It's no longer a TEM wave. And that's equation 10.7 in his book. I'm not going to quiz you on that. Just be aware of this. With all microwave devices, there's an upper frequency, or microwave designs for transmission lines on Doroid board or any kind of a board material. There's an upper limit. Got me on that? Just keep that in mind. It's usually not even it's going to be so high most of the time you don't even think about it. But nowadays, with automotive stuff, they're going to 77 gigahertz for the frequency, the radar frequency for cars, for collision avoidance. That's starting to approach the point where you have to pay attention to that. Matter of fact, it might be something you have to pay attention to depending on how these, what kind of boards you're using. For FR4, you probably do. FR4 is cheap stuff that they use. It's that green board that you see that's got like all sorts of copper. You see copper on top all over the place, and you mount chips on. FR4 is lossy. It's low frequency. Now, he gives you some design parameters and attenuation. Don't worry about that. Not at all. I feel this is sort of like the fiber optic stuff. All right? Really, we can't dig that deep, and it's not really in our best interest to dig that deep here. Here's where it's in our best interest. How to go about actually doing filtered, or really doing impedance matching with this thing. Because let me just tell you this. In the real world, I may have an antenna that I mount. Usually everything's mounted on these things with a coax line first. Right? You get a coax cable, it's cinched to the board, and then it comes in there and it's fed by a transmission line. Well, if you don't have impedance matching there, it's very bad. So how do you impedance match something where you might have transmission line of 200 ohms characteristic impedance, and then you've got a device of like 50 plus J10, and you only got a little bit of space? You can't run long lines, follow me? I can't have I'm trying to minimize the amount of, they call it footprint space that I'm using, how much space I use on this. Remember, anytime we do shunt stub tuning and stuff, we basically have to create a transmission line, don't we? That can be very bad when you're talking about microwave engineering. So they actually use components that they stick in there, really small capacitors and inductors, typically capacitors, because inductors are more of a problem radiating. So here's how they do it, and I'll just show you this. I want to impedance match this, and here's my load that I want to impedance match using microwave tricks. That's got some ZL, and I've got a transmission line over here with some Z naught. Now, in the past, when you did this, it depended if it was a shunt or series connection, right? And I'm going to just draw a Smith chart here. I really am going to try to do this in a way that's best for everybody. So my Smith chart doesn't look good, but it's a Smith chart. So here, R is 1, that's infinity, and that's 0 as far as the values. And this is J1, right? And this is minus J1. And we know if we have ZL, and we come in the Smith chart at any point, say here, then there's a couple ways we can deal with it. If we've got a series connection, right? I'm just going to talk my way through it. This is bringing it back. I would take this and I would draw. This would be the same radius all the way around here, and I would move from here, my point 1 to point 2, right? And then I'd figure out how far I moved. Y'all with me? Now I move down to here, and then I'd figure out what impedances I'd add. And if this is 1 plus JX, which it is, right? Because it's on a one circle, it would be 1 plus JX. Remember, that's normalized, right? Maybe I should say this. Normally, my point 1 is ZL, which is capital ZL over Z naught. Then I move to point 2, which is here, right? And I move this far, call it L through, right? Now, if I have 1 plus JX that's normalized, obviously you realize that I can do a couple of things. If I put in minus JX normalized here, then I'm impedance matched, correct? That's one way. And that's in series. If it was in parallel, I'd go to the admittance domain, and I'd find admittances that would do that, right? I'm just making sure everybody's clear about that. So now I'm going to show you how we do it with microwave engineering. And here, we don't move. Now, this is important. We're not going to be moving around, sticking stuff away from the load. We're going to put everything on the load, and I'll show you how. So here's how we do it, impedance matching with microwaves. And we do this with both parallel and series connections, but we call them L section matching. The reason we call it that is if we have a load over here, I'm going to show you how. Our matching will either be an inductor in series, a capacitor in parallel this way, which looks like an L, or you're going to see a capacitor in series, an inductor in parallel, or you're going to see something we got a parallel and a series. In other words, all the elements you add are right at the load. Got that? There is no, I gotta move so far, which is real important. I mean, there is no long stubs. Everything is gonna be attached to load. So let me go through this with you and why it's so important. So if I have some impedance here, ZL, and I want to impedance match it to something Z naught, but I don't want to move and have shunts and stuff like that. What I do is this. I'm going to go and draw my transmission line. Or draw my Smith chart, pardon. First thing I always do when I'm doing this matching, this is going to be impedance matching. Let's find ZL, which is capital ZL over Z naught. And now there are three possibilities, and I'm going to show you something. This is something you haven't seen yet. In his book, he shows us first on page 552. This is called a rotated Smith or rotated circle Smith chart. So then there's going to be a circle here. I didn't draw that very well, but this circle is identical to this circle. It looks like this. You take that circle and just rotate it and stick it here. Follow me? Mm-hmm. This is called a rotated circle. Okay. Now, when we do this right here, there are three possibilities. The first is that this thing can be inside the one circle, right? It can fall somewhere inside this. The second possibility, it can be inside the rotated circle. And the third, go ahead.
What's inside?
ZL. A ZL would have some value, would be like A plus JB. Well, A plus JB could land here, it could land here, or it could land outside of both. So the first possibility is it's inside the rotated circle. So for this one, this is first possibility, and that is ZL inside R equals one circle. Well, if it's inside the R equal one circle, I want you to just work with me on this. Let me pick a value so I can show you. Suppose I just say anywhere inside is good, but I'll make ZL equal to like 2 plus J1. All right, that's the R equal 1. The R equal 2 circle is right here, right? I mean, not drawn very well, but you get the idea. What I'm trying to do is show you that this would be R equal 2. Do you agree with that? Roughly. And then I got plus J1. Well, J1 is this one. So it's roughly here. That would be ZL. Y'all follow me? Now, if I think about adding something in series with that, we're in the impedance domain there, right? Please be clear about this. If I add any impedance to that, it's going to be a plus or minus J something that is normalized. Do you agree? But the best I can do is get rid of this J1, right? My goal is, when I'm done with everything, I either want to normalize Y or normalize ZL that has a value of 1 and only 1, right? That's what impedance matching is all about, right, guys? So no matter what I add in series, it does no good. Follow me? I can't get it to a value of 1. So I go to the admittance domain. So ZL is inside the arc of 1 circle. I immediately go to YL. And that's going to be 1 over ZL. Now, I'll just try to estimate this. If you have a calculator and you can help me, it'd be greatly appreciated. If you take 2 plus J1 in your calculator, take 1 over that and give me the real and imaginary part. I know the magnitude of this is really square root of 5, right? And then it's at an angle of 35 degrees, 30 degrees, something like that. Anyway, I want it in real and imaginary. So 1 square.
It's 0.4 minus 0.2 J, or J 0.2.
All right. 0.4 minus J.2. 0.4 is, if you look, the way you get this point here, you just go through the conjugate point, draw a circle. If that's ZL, this would be YL, correct, class? Now, I'm in the admittance domain, right? I went from here, this is my first point, to there. I'm in the admittance domain. So I went from point 1 here to point 2 here. This is the actual progression. So that's 1, then 2. Now, hear me. If I'm in the admittance domain, I can add something in parallel, right? If I add an admittance in parallel to this thing, hear me now. Remember, if I'm adding admittance, I can get this thing, I'm trying to draw this here. This has a real part of 0.4, so y'all see I'm trying to show you this is the circle that would have 0.4 is the radial distance, right? Now look, I can add a plus or minus J something and hit that point, or hit that point. Y'all follow me? Now when I'm at that point, just go with me on this. Why do I want that? Because if I take 1 over that, now I'm on a 1 circle. Got that? Y'all with me? So that's the goal. I'm inside here. Anything I add, I can't get to the 1 circle by adding anything in series. So now I go to the admittance domain. Now when I'm here, I can add either this or this. Typically, we like capacitors, just saying, if it's in parallel. We like capacitors in parallel for one reason, because they don't pass DC. And oftentimes, with circuitry, microwave circuitry, we have a DC offset. You know, with your like BJT transistors, you have to get a DC current going through those that set the bias, right? With FETs, typically, it's basically a capacitor, so you don't need that. But with BJTs, you do. And so I'm just telling you this much, that you'd never want, if you can at all avoid an inductor in parallel with the load. You always want series for an inductor because it'll allow DC current to flow, and a capacitor in parallel. Follow me, guys? All right. So what does that mean? Well, this is admittance. I know I've got normalized admittance. The impedance of a capacitor is 1 over J omega C, right? The admittance is what? J omega C, positive J. So if I add a capacitor, I'd be moving from 2 to 3 here. Correct, class? I'll get to all the exact nature of this. And then when we're here, now we go to the impedance domain. So we add that element, and I'm going to do this whole thing for you, but I want you to see the process. Now I'm going to go back to the impedance domain. Remember, I'm going to add a capacitor right here. I'll figure out what it is in 1 second. In parallel. I'll do this whole thing. I just want to make sure you, up here you get this. And now I'll be on the 1 plus J something, right? Notice this, it's going to be 1 actually minus J something, isn't it? Because it's below the equator, right? 1 minus J something. So what do we add in series? Now we're in the impedance domain, an inductor. An inductor's impedance is J omega L, right? Now I'm going to do the whole 9 yards of this thing. But I want you to see the process. And again, this is how you go about it if the initial point is inside the 1 circle. Now, if the initial point is outside 1 circle, then the first thing you do is, in the rotated, I'll go through this one in a bit. You add an impedance, get to this point, and go over here, and then add an admittance. But I'll do this one, but just so you see the process. If it's outside of either of those, it doesn't matter what you do. And I'll show you that one too. So this is real microwave engineering. Now we're gonna do the actual problem. And I gotta show you how to get the normalized value of the capacitance and inductance. So what I'm going to do is example 10.2 on page 551. He says he's got a 50-ohm transmission line, which is about normal. So we have Z naught equal to 50 ohms. And then he has ZL equal to 250 minus J 250 ohms. And he wants to develop an L section matching network. With me? Let me try to do it. It's in the book, but I want to just go through the steps. So here's my big old Smith chart. Here's the one circle. Here's the rotated circle. I'm going to draw on the scale to get the idea. And now the first thing I do is plot this, where I get ZL. So ZL is equal to capital ZL over Z naught. This is the normalized impedance. And that's 5 minus J5, correct? Now you can see that that's inside the one circle, right? Whenever the real part's less than 1, you're inside the one circle, correct, class? Or I should say the real part is greater than 1, my bad, greater than 1. So here 5 is somewhere like this. You look up, it's about there, right? And then I got minus J5. Well, minus J5 is here, so the point is somewhere in here. This is going to be 5 minus J5, right? That would be the first point, and that's ZL. Y'all agree with that? Obviously, it's inside the one circle. Nothing I add in series will help me. So I need to go to the admittance domain. I take 1 over that. And I come up here. And this will be 0.1 plus J 0.1. The reason I know is because I look. You can do it if you don't believe me. It's in the book. So that's the first point. Here's my second point. Really, 2. And this is YL. Now I have a choice. I know I've got a real value here, 0.1, and if I look at the 0.1 real part, it does this, right?
Almost.
Man, this knee's been bothering me. I ran at lunch. Boy, I had a torn meniscus there, so I had surgery. And every once in a while, I think the weather, people tell me that. I don't understand how that works. How can moisture outside of my body affect the inside, but it seems to. Anyway, so I have 0.1 plus J.1. Now, if you look in your book or look at a Smith chart, and I'll give you some of these. I'll send you a rotated Smith chart and print some off. If I move from here to here on that one, I'm going to intersect this rotated circle. And it's going to have a real value, this is 0.3, of 0.1 plus J, and we're going to take a look at that. He shows this to you. 0.1 plus J.3. Y'all see it? This is actually going to be third point right here would be 0.1 plus J 0.3. Are you with me? Guys? Now, how much did I add? Well, I had 0.1 plus j.1, right? I got to j.3. That means I added j.2. Isn't that right, class? That's in parallel. So now I'm going to say I have a normalized admittance here of j.2. I could have gone down here too to 0.1 minus j.3, but I'm adding a positive j because I want a capacity. Okay? And I'll show you how to calculate the value in a second. Now I'm going to go from here. Somebody can help me here. That's my third point. Now I'm going to go from there down to this point right here. And this is the fourth point. It's 1 over that. It probably gives the value. It's 1 minus j3. So right here, remember that was y. I went from here to here. Now I'm in z, and that's 1 minus j3. You see that? Right? 1 minus j3. Well, that's normalized impedance, right? I need to add a plus j3. I know that's going to be an inductor. So that means over here, I'm going to have a series J0.3, and then I'm impedance matched. Got me? Now remember, those are normalized. So let me show you how this normalization works. First, I'm going to talk about the J.3. You see, that's an impedance, right? It's in series, correct, class? Well, think about it. For an inductor, in general, an inductor has an impedance of J omega L, right?
0.3 or 3?
Where? It's 3. I put 0.3, I'm so sorry. This should be minus J3. I'm sorry. My bad. So that's the impedance, right? To normalize it always means to divide by the characteristic impedance. So if I divide this by Z naught, now I have the normalized impedance, right? What do I want that to equal? 3, right? So it's J3. And therefore I can say L is simply equal to 3 Z naught divided by omega. Y'all follow me? Okay? All right. Everybody good with this?
Mm-hmm.
Did you have a question? Want to make sure I'm good. Are you good with this? All right. Now, how about over here? That's an admittance, right? Here's the way I do this for you guys, because a lot of people, the admittance stuff, you don't use all. I know that for a capacitor, the capacitor has an impedance of 1 over J omega C, right? You can work with this one. Do you all agree with that? Capacitor. Now I'm going to normalize it. That means I divide by Z naught, right?
Mm-hmm.
Now that's still a normalized impedance, right? But that's an admittance value, so now I take 1 over everything, and now I say J omega C times Z naught. Well, that's what J.2 is. Y'all with me? So that's equal to J0.2, or I can say that C is equal to 0.2 over omega times Z naught. And that's how you would calculate the values of L and C to impedance match this. Now, something I'm going to state. This impedance matching only works for a very small band of frequencies. Remember, the minute the frequency starts changing, then these values, the J.2 starts changing. You with me? And that's why you got to be careful. Now, without getting into a whole lot of it, If your load impedance has the same ratio of change, the real and imaginary part, as the line filter, then you don't have to worry. But frankly, most of the time, any kind of impedance matching works for one and only one frequency in a very narrow band about that frequency. All right, so keep that in mind. Wideband radar stuff and all that, you can't use this. There's other methods you have to use, and that comes later. I didn't get a chance to do one with inside this, but here, because if the normalized impedance landed inside the rotated circle, no matter what I added to that, I would add an impedance first to get it to this rim, and then I would add an admittance. So it'd be the opposite. Before, what I just did is what? When the load is really, the normalized impedance is inside the one circle, or the load's magnitude is greater than Z naught is what it comes down to, I have to put something in parallel first, then in series. See how it was parallel first, then the series? Well, if the load impedance magnitude is less than the characteristic impedance, then you add an impedance first, then admittance. And you'll see this when I give you problems, okay? I'll give you some problems. Yeah. Go ahead.
How did you get rid of the 1/JWC?
Well, this is impedance, right? That's normalized impedance of the capacitor, right? I'm worried about admittance 1 over that, right?
Okay.
That's how I got it. Are you with me? All right, I'll give you some homework. Hang in there. It's not as bad as it sounds.